In this presentation, you will learn ways of analyzing categorical data. This covers Chapter 4 of your course textbook. I've already introduced you to categorical variables, but as a refresher, remember that they can be data elements that are either nominal or ordinal. For example, gender, discharge status, admission source, or MSDRG codes, they are all categorical variables. A very common type of categorical variable is binary values, which can take on only two values. Commonly, they are coded as yes/no responses. For instance, does a patient have a family history of cardiovascular disease? Yes or no. When considering the ways in which variables are analyzed, they are commonly understood based on the proportions of responses. That is, you may find that of all your patients that were seen within the last year, 85% had a family history of cardiovascular disease, while 15% did not have a family history of cardiovascular disease. The descriptive statistics of categorical variables are commonly employed using frequency distributions, contingency tables, and ranks. We will look at each of these a bit closer. Frequency distributions are often used as a way to determine the number of times a variable occurs. For instance, we may want to know how many male and female patients were seen by a specific physician last week. Of the 56 patients seen last week, you may have found that 32 were female, or 57%, and 24 were male, or 43%. You can also examine the data with a graph called a frequency chart. A bar plot is an easy way to quickly show the differences in the number of female and males that were seen by this particular doctor last week. Alternatively, a pie chart can be used for displaying differences. I will note, however, that a pie chart requires a reader to interpret the data based on the area of each group. It is actually perceptually easier and more efficient to use a bar plot. Readers are able to interpret bar plots much faster and more accurately. Next, a contingency table is a valuable method for displaying the relationship between two categorical variables. Suppose we wanted to know whether those patients we looked at previously were discharged to their home or not. We can show a contingency table or a cross-tabulation of the patient gender and the discharge to home variable. Contingency tables are often referred to by the number of rows and columns. The example I used is a 2x2 contingency table. The grand total for the rows and columns are not counted, and the title columns are not counted. Rank refers to a value's position in a group relative to other values that have been organized in order of magnitude. It is a great way of summarizing ordinal data, but cannot be used with nominal data, since it does not have any inherent order. Percentile ranking is commonly used for describing the distribution of data. For instance, let's say we wanted to separate mortality scores into 4 different groups to better understand the relationship of all values to each other. We can use percentile ranking to do this and separate the data into 4 quartiles. The 4 quartile stretches to the 25th percentile of the data, the second from the 25th to the 50th percentile, the third goes from the 50th to the 75th percentile, and the fourth from the 75th to the 100th percentile. In a similar fashion, we could opt to separate the data into 10 equal chunks based on deciles. So let's say we have a patient that has a mortality score in the 54th percentile. That is, a patient's mortality score is equal to or greater than 54% of all the other patients. This may be helpful when predicting mortality risk based on a score. Let's examine inferential statistical methods for looking at categorical data. First, let's begin by simply defining statistics. Statistics is the science of collecting, organizing, interpreting, and learning from data. Usually, we wish to learn about a population of interest using data collected on a sample. We use statistics as a way to estimate an unknown parameter of a population. To clarify, a population is the entire group of individuals in which we are interested but cannot usually access directly. A parameter is a number describing a characteristic of the population. Conversely, a sample is a part of the population that we actually examine and for which we have data. A statistic is a number describing a characteristic of the sample. Thus, the results of our statistical test will provide us with a statistic that we can use to estimate an unknown parameter in order to get the best approximation regarding what would happen to a population. There are three common data distributions that can be visualized using a histogram. The one all the way to the left is a normal curve. The mean and median should be almost the same number. This is the distribution we attempt to achieve most of the time. A positive skew is the one that tails to the right. The mean is typically greater than the median in these cases. Oftentimes, we will transform positively skewed data in order to achieve a normal distribution. One common transformation method is called a log transformation, where you take the natural log of all the numbers in your data set. When you plot the log transformed data, it should be closer to a normal distribution. A negatively skewed data set has tailing to the left. In this case, the mean is typically less than the median. A transformation method for negatively skewed data typically involves taking the log of 1 plus the maximum data value minus the data value for each row. You won't have to do this in this class, so we won't be discussing that in any particular depth. When stating a hypothesis, there exists both a null and alternative hypothesis. The null hypothesis is actually what the statistical procedure is testing. When you have a significant p-value, then there is enough evidence to reject the null hypothesis and accept the alternative. With statistics, we are testing if things are the same as each other. The alternative hypothesis is accepted if the null is rejected, and we can state that things are different from each other. For many procedures, there are two types of alternative hypotheses. These are important to differentiate because they can significantly change your p-value. A one-sided hypothesis provides directionality for a relationship. For instance, a one-sided alternative hypothesis may be patients taking drug A have a lower blood pressure than patients taking a placebo, or females have a greater GRE score than males. A two-sided alternative hypothesis does not provide directionality. For instance, patients taking drug A have different blood pressure levels than patients taking a placebo, or females have different GRE test scores than males. The advantage of the two-sided hypothesis is that we don't need to make a prediction regarding the directionality. If we incorrectly predict directionality, such as females have higher GRE scores than males, but in reality, males have higher GRE scores than females, we would actually get a very high p-value and see no significance. However, if we were to have used a two-sided hypothesis, we would have seen a difference. By default, we typically stick to a two-sided hypothesis, yet in certain circumstances, you may use a one-sided hypothesis. When using a statistical test to compare the means between two groups, like we already stated, there is a one-tailed or two-tailed test. The difference between a one- and two-tailed test is based on the assumption of which way you think the differences between the two groups will occur. A one-tailed test for the possibility of a relationship in one direction, while two-tailed tests for a possible relationship in both directions. For example, Group 1 has a greater average than Group 2 for a one-tailed, versus Group 1 has a different value than Group 2 for two-tailed. Again, the consequence of choosing a one-tailed or two-tailed test is that if you predict in the correct direction, your p-value would appear smaller. However, if you're uncertain which group would have a higher or lower value, you may also miss a significant difference if you predict in the wrong direction. clarify the difference, let's actually look at a couple examples. Let's say you wanted to compare the weight of subjects that either take a placebo or a new weight loss drug. You can opt to predict that the weight loss drug would lead to a decrease in weight and therefore use a one-tailed test. If, however, the weight loss drug caused a drastic increase in weight, you would not detect a significant difference in the direction if you stayed with that one-tailed test. Let's say you wanted to compare the time it takes to complete a progress note with either an electronic health record or paper. You don't really have enough evidence to predict the directionality or the differences, so you opt to stay with the two-tailed test. You are testing whether the mean time to complete a note with an electronic health record is different than with paper, rather than predicting if an EHR leads to faster note completion. That, in contrast, would be a one-tailed test. The test statistic is the value that is calculated from a specific statistical procedure. The test statistic is compared against the available probability distribution to determine the probability of making an error when you reject a null hypothesis. There are two types of errors that can arise in this process, a type 1 and type 2. A type 1 error occurs when through your research the null hypothesis is rejected and you find the alternative is true when the null hypothesis is actually true. That is the frowny face in the bottom left box. A type 2 error occurs when the null hypothesis is not rejected, or your research finds the null hypothesis true when it is actually false, and the alternative hypothesis is true. This is the frowny face in the upper right box. A type 1 error is set prior to performing your hypothesis test and is called the alpha level. Now, the alpha level of a test should be set based on the risk of cost inherent in rejecting the null hypothesis when it is true. Typically, the alpha level is set as 0.05, but can take on a value of 0.1 or 0.01. A p-value is a result of your test statistic, and you can confidently reject the null hypothesis when your p-value is less than the predefined alpha. A type 2 error is also known as beta and is affected by the sample size. A larger sample size will decrease the level of type 2 errors. Your book suggests that there are 5 steps in testing statistical hypotheses. I wanted to stretch these 5 steps out into 10 steps that must be followed in order to effectively analyze data and do experiments. The first is to specify the question to be answered. This question must be specific enough that a person can understand what it is you're doing. For instance, the following is a bad research question. Do females do better than males? Many of you might think this suffices and be quick to answer yes. But there's problems with this question. First, do females do better than males in what? Also, what do you mean by better? A clearer research question would be the following. Do females have higher GRE scores than males? Now we know what we're comparing and leave out subjective terms like better. The problem with the word better is that we must leave it up to the reader to interpret the meaning of the term. Better may mean a low score, as in golf, or a faster time, as in running, or a higher score, as in the GRE. It's context dependent, and we shouldn't leave it up to the reader to interpret. The next step is putting the question in the form of a null hypothesis and alternative hypothesis. The format of the hypotheses depends on the statistical test you are conducting. Generally, the null states that things are the same. In our GRE example, the null hypothesis would be females and males have the same GRE scores. The alternative hypothesis states that things are different. For instance, females and males have different GRE scores. We could be even more specific and say that females have a higher GRE score than males. However, by providing directionality to our alternative hypothesis, it may change the significance. That would be a one-tailed hypothesis versus a two-tailed hypothesis. The next step involves putting these hypotheses in a statistical form. The null might look something like the GRE for male is equal to GRE for female, while the alternative might be GRE for male is not equal to GRE for female. Again, the format really depends on the statistical procedure being used. The fourth step is to determine which variables are relevant to the question. When collecting data, you oftentimes collect a lot of data. Therefore, it's a good idea to figure out which variables you want to use in an analysis. For the purpose of our GRE example, you would obviously want to collect information about GRE scores and gender for each subject. The next step is to determine what type of variables you're working with. Well, GRE is a nominal quantitative variable, while gender is a categorical variable that can take on the values of either male or female. Next, choose the statistical test you want to use. In all actuality, you should have conducted this step prior to developing your null and alternative hypotheses, because their format is dependent on the statistical test being conducted. The GRE example could employ a two-sample t-test to compare GRE scores for males and females. The next step is to do the experiment in order to collect the data. That's easy, right? The next step is to determine if the data you're using in your statistical procedures meet the assumptions of the statistical test. If it doesn't, you should choose a more appropriate test. We will talk about these assumptions in some detail in the subsequent sections. Now you can apply the statistical test and interpret the results. Finally, communicate your results using clear, effective language in graphs and tables. It is important that you don't overdo the graphs and tables. Only stick to the things that are necessary. Don't show the exact same data in two different graphs. Use the most effective graph to communicate the results. We will discuss some aspects of data visualization that will point some of the advantages and disadvantages of particular graphs. Now we're going to cover some of the statistical procedures you can use to analyze categorical variables. The first we will talk about is the chi-square test of independence. The chi-square test is used to test for relationships between categorical variables. The test is quite easy to calculate by hand, but it's much easier and less error-prone to use software. The first step is to state the null and alternative hypotheses. For a chi-square test, the null hypothesis is that there is not an association between variables. That is, the variables are independent. Conversely, the alternative hypothesis is that there is a relationship between variables. Let's go back to our example with evaluating gender versus discharge to home. The null hypothesis would be that there is no association between gender and discharge to home, while the alternative hypothesis is that there is a relationship between gender and discharge to home. With the chi-square test, we want to determine if the results from this sample can be generalized to conclude a difference in proportions sent home in the two genders. Remember those counts we saw earlier? We'll use this data when using a chi-square test. Pay particularly close attention to the row totals and grand totals. A chi-square test statistic is calculated based on the sum of squared observed frequencies in the cell row I in column J minus the expected cell frequency in row I in column J divided by the expected cell frequency. Let's do this by hand so you get the idea. It's not as complicated as it looks. The first thing we need to do is calculate the expected cell frequencies for each cell. To do this, we go through each of our 4 cells that make up our data. For each of those cells, look all the way to the right for the row total, and multiply that by the grand total all the way in the bottom cell. Then divide that number by the grand total number of patients. So for females that were discharged home, we take the row total for females, 32, and multiply that by the column total for the number of patients discharged home, 30, then divide that number by the total number of patients, 56. Move on to the next cell to the right, take the row total for females, 32, times the number of patients not discharged home, 26, divided by the total number of patients. Now we do the same for males. Take the total number of males, 24, times total number home, 30, divided by the total number of patients, 56. And lastly, the total number of males, 24, times the total number not at home, 26, divided by the total number of patients, 56. Eventually, you end up with the expected cell values for each cell. We will use these values for calculating the chi-squared statistic. So now we need to know the observed values. These are the actual counts for each of the cells, and the expected values. These are the numbers we just calculated. For each cell, we will do the following. We will take the observed value minus the expected value. We're going to square that number, and then divide the number by the expected value. So for females that were discharged home, we would take the observed value of 20 minus the expected value of 17.1, which is equal to 2.9. If we square that value, it comes out to 8.41. Next, we divide 8.41 by 17.1, and we get the value of 0.49. If you were to do this same thing for each cell, and then add up each of those values, you would obtain a chi-squared statistic of 2.39. To determine if our chi-squared statistic is indicative of a statistically significant result, we must compare the test statistic of 2.39 to a chi-squared distribution table with 1 degree of freedom to determine the probability of incorrectly rejecting the null hypothesis if it is less than our defined alpha of 0.05. That is, we are calculating our p-value. If we find the p-value is less than 0.05, we can conclude that there is statistical significance and the two values have a relationship. First, we need to calculate the degrees of freedom. First, you take the number of rows, 1, times the number of columns, minus 1. In our example, there are 2 rows, males and females, and 2 columns, home and not home. Therefore, our degrees of freedom comes out to be 1. If we take a look at the chi-squared distribution table, we need to find where our test statistic of 2.39 fits. You can see that our test statistic is less than 2.706 and less than 3.841 and all the other critical values. Therefore, we have to conclude that the p-value for our test is greater than 0.1, therefore suggesting our result is not statistically significant. If we had calculated a test value greater than 3.841, we would have achieved statistical significance. Based on this test, we do not have enough evidence to reject the null hypothesis. We must conclude that there is no evidence that the two variables are not independent. The next statistical procedure we're going to cover is a one-sample z-test for proportions. This is an appropriate test to adopt when you want to compare some rate to a standard or known rate. For instance, let's say we wanted to determine if the flu vaccine compliance rate for employees at a hospital were significantly different than the goal. We could use a one-sample z-test. If we use our example of a hospital that has a flu vaccine compliance rate for employees at a 70% and the company has a goal of 85%, we might want to ask, is there a real difference between the observation of 70% and the goal of 85%? The one-sample z-test is appropriate in this situation. We only have one group that we are comparing to a standard or known value. The one group are the employees and vaccination rate, and the known is the goal rate of vaccinations. We can either choose to use a one-sided or two-sided z-test. One-sided would be completed by stating our null hypothesis to be that the observed proportion is less than or equal to the standard, while a two-sided null hypothesis would be stated by saying that the observed proportion is equal to the standard. Let's stick with the two-sided z-test. Therefore, our null hypothesis is that the observed proportion is equal to 85%, and our alternative hypothesis is that the observed proportion is not equal to 85%. Next, we have to set our alpha, which we will set at 0.05. Then we need to select our one sample z-test, which uses the formula shown on the slide for calculating a test statistic. We can use statistical software to do the rest and show us our p-value, or we can use a distribution table for determining if there's a difference. As you can see on the slide, if we calculate the z-value given our observed proportion of 0.70 compared to the goal of 0.85, we obtain a value of negative 1.36. In order to obtain statistical significance for a two-sample test, we need to have a z-value that is greater than the critical value of an alpha of 0.025. That critical value we need to beat is 1.960. So if we take the absolute value of our test statistic, we do not beat the 1.960. Therefore, we cannot reject the null hypothesis. If you were using stats software, you wouldn't have to calculate the p-value by hand. Therefore, you would be able to quickly determine if your observed p-value is less than the alpha. In the case of this example, the p-value would be greater than 0.1. Our conclusion is that there is not enough evidence to conclude that 70% rate observed in the sample is statistically different than the goal of 80%. Therefore, even though the 70% rate appears lower than the hospital's goal, they should be happy because it isn't statistically lower. In addition to testing the hypothesis that a proportion is different than a standard value, you may also wish to determine a range of reasonable values for the population based on these sample values. This is where a confidence interval can be used. A confidence interval reports a proportion plus or minus a margin of error. We often talk about confidence intervals in terms of probability, that the confidence intervals contains a true population value of the proportion. This is referred to as the confidence level and is most often reported as the 95th percentile confidence interval. That is, we are 95% sure that the calculated confidence interval contains the true population proportion. To clarify, let me provide an example using the vaccination data I mentioned earlier. The P is our observed proportion from our sample, which in this case is 70%. That is, 70% of the observed hospital employees received the flu vaccine. Let's see that we decided to use a confidence level of 95%. Therefore, the critical value for the confidence level is 1.96, which we can derive from the standard normal distribution critical value. This is shown on page 69 or table 4.8 of your text. Also, the sample size for this study was 10. That is, 10 employees were asked if they received the flu vaccine. The first thing we need to do is take 1.96 and multiply the number by the square root of 0.7 times 1 minus 0.7 divided by 10. The result is 0.28. Next, we need to determine if the upper and lower extremes of our confidence interval, also known as the margin of error. To find the lower extreme, we take 0.7 minus 0.28 and get 0.42. To find the upper, we take 0.7 plus 0.28 and get 0.98. The result is that we are 95% sure that the interval from 0.42 to 0.98 contains the true population proportion of flu vaccine compliance. The next statistical procedure we're going to cover is a two-sample z-test for proportions. The purpose of a two-sample z-test is to compare differences of proportions of two distinct groups. For example, if we wanted to compare the proportion of drug use amongst teens in Wisconsin compared to Minnesota, we could use a two-sample z-test. Again, I want to emphasize that with a two-sample z-test, you are comparing two distinct groups. The responses in each group are then independent of those in the other group. Remember, when you conduct a statistical test, the test is assessing the accuracy of the null hypothesis. You either accept or reject the null. Thus, it's always a good idea to consider what the null hypothesis is prior to conducting a statistical procedure, and also consider the alternative hypothesis. In the case of the two-sample z-test, the null hypothesis would be the proportion from sample 1 is equal to the proportion from sample 2. Consider this for a moment. If you wanted to compare the proportion of surgical patients with a hospital-associated infection versus the proportion of non-surgical patients with a hospital-associated infection, the null hypothesis would be that the proportion for surgical patients with a hospital-associated infection is equal to the proportion of non-surgical patients with a hospital-associated infection. The two-tailed null hypothesis would be the proportion from sample 1 is equal to the proportion for sample 2. Thus, the two-tailed alternative hypothesis would be the proportion from sample 1 is not equal to that proportion for sample 2. If we wanted to add directionality, we could, yet this might cause problems if we predict incorrectly. So after you define the hypotheses, the next thing to do is to calculate the z-statistic. Then determine the p-value, followed by making a conclusion. Rather than calculating the z-stat by hand, we're going to use software to do it for us. The conclusion would be whether you accept or reject the null hypothesis. Let's assume there is a difference in the proportion of surgical patients with a hospital-associated infection and a non-surgical patients with a hospital-associated infection. The conclusion can be stated as such. There is enough evidence to reject the null hypothesis, which suggests that there is a significantly greater proportion of surgical patients with hospital-associated infections than non-surgical patients. There are two assumptions that must be met when you conduct a two-sample z-test. The first assumption is that the groups are comparing are independent random samples. This simply means that each group is distinct, but you randomly select in order to minimize bias. For instance, if you were to compare infection rates in surgical and non-surgical patients, I would randomly select surgical patients to be in one group and randomly select non-surgical patients to be in another group. I would not bias the selection by only using surgical patients from an exceptional surgeon. The second assumption is that the groups are normally distributed. That is, we aren't only comparing the super sick and a couple super healthy people. We want to assess differences in groups that, when you take a look at a histogram of each group, it looks like it's a bell-shaped curve. The reason for this assumption is that we are comparing means and proportions that are representative of a sample when it does not fit a normal distribution. So let's take a look at the example of the two-sample z-test. Let's say we wanted to investigate whether or not the inpatient mortality rates are different for patients with heart failure and shock, with major complications and comorbidities, as determined by being coded with MSDRG code 291, versus those with no complications or comorbidities as determined from being coded with MSDRG code 293. We find that MSDRG code 291, heart failure and shock with major complications and comorbidities, occurred in 360,972 discharges, with 19,670 deaths, or 5.45% of the patients died. For MSDRG code 293, heart failure and shock without major complications and comorbidities, there was a total of 197,734 discharges and 2,148 deaths, or 1.09%. We want to know if the proportion of deaths were significantly different between the two groups. Our two-tailed null hypothesis is that the proportions between the two groups are the same. Our alternative is that the proportions between the two groups are different. We set the alpha at 0.05. Next, we calculate the z-stat using the equation found on the previous slide. Of course, we would have to use software to do this for us, so I won't go through all the math, but the math is worked out on the slide, and we obtain a z-stat of 80.5. And after looking that value up in our normal distribution table, we find that our p-value is less than 0.05. Therefore, we have enough evidence to reject the null hypothesis and conclude that the mortality rate for patients assigned to MSDRG 291, heart failure and shock with major complications and comorbidities, is significantly different than that assigned to MSDRG code 293, heart failure and shock without major complications and comorbidities. One of the main things I want you to know is when you should use a particular statistical procedure. Therefore, I'm going to offer you some hints when you need to choose which statistical test to use for analyzing categorical variables. A chi-squared test is used to determine if there is a relationship between two qualitative variables. A one-sample z-test is used when you're comparing one group of proportions to a standard or goal proportion. A two-sample z-test is used when you're comparing proportions between two different subjects in two different groups. For our next topic, we will be discussing how to analyze continuous variables.